All right, so today what we're looking at is the Earth's interior. Now, if I were to take the Earth and, because I'm super strong, rip it in half, or slice it in half, and I was to look at a cross-section of the Earth, so that's what that is, a cross-section, I can see that the Earth's divided up into basically four main layers. So the blue would represent the crust, and that's actually thicker than the crust really is on here, but the blue represents the crust. The orange represents the mantle, the red represents the outer core, and the yellow represents the inner core. All right. Now, the mantle's broken up into different layers of the mantle, stiffer mantle, plastic mantle, and so forth, but the overall it's just called the mantle. All right, now, the different layers have different characteristics to them. And things that we know about the layers, the crust, the mantle, and the inner core are solid, while the outer core is a liquid. Now, we've never drilled anywhere near that deep. We've only ever drilled down, the Russians drilled down to like 7 miles down. It's the farthest anyone's ever drilled. So a lot of the information that we have is about what we think the Earth is like that far down is inferred data, or inferred conditions from data from seismic waves or PNS wave data from earthquakes. When earthquakes happen, they give off shock waves, different types of shock waves. They react differently when they travel through solids and liquids. So by studying these earthquake waves, we can figure out what layers of the Earth are liquid and what layers are solid. So that's where we got the information from. All right, now, by far the thinnest section of those four is a crust. And the crust is not a uniform thickness throughout. Some places the crust is thinner, and other places it's thicker. The ocean crust is the thinnest. Relatively speaking, it's 5 to 7 kilometers thick, which may sound thick to you, but it's quite thin compared to the continental crust, which is substantially thicker, on average about 30 to 40 kilometers thick. So continental crust is roughly about 6 times thicker than oceanic crust. As far as the composition goes, ocean crust and continental crust are made out of different stuff. Ocean crust has comes from mafic magma or mafic lava, where continental crust comes from felsic. And that has a different set of elements in it. Mafic minerals have a lot of iron and magnesium in it, where felsic ones have lots of aluminum and silicon. And the result is mafic or oceanic crust is higher in density, continental crust is lower in density. The oceanic crust has a density of around 3 grams per cubic centimeter, or continental crust is about 2.7 grams per cubic centimeter. Now, the interior Earth, the core, is actually not made out of rock at all. The core, we believe, is made out of metal, specifically from iron and nickel. Now, again, we've never drilled anywhere down that far, so what would make us think that? Well, actually, it's not from looking down, but from looking up. If you remember back in astronomy, we had the planets. We got Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. And between Mars and Jupiter, there was something located between Mars and Jupiter. And what's located between Mars and Jupiter is the asteroid belt. Now, what a lot of scientists think is that asteroid belt is the remains of a terrestrial planet. So that used to be a planet like these guys right here. Mercury, Venus, Earth, and Mars. They're all rocky planets. They have surfaces. You can land spacecraft on them. They think that this was a planet like those guys right there. And what happened is, at some point in the planet's history, it may have got struck by a meteor or struck by a comet, or maybe the gravity from Jupiter had some influence. But this planet got ripped apart. So basically what's orbiting the sun now are a bunch of pieces of a broken up planet. Now, every once in a while, those pieces leave its orbit, and a lot of them go crash into Jupiter because Jupiter's really big and it's right next to it. Some of the pieces crash into Mars, and some of the pieces crash into Earth. Now, most of those pieces, about 85% of those pieces are made out of rock, but about 15% of them are made out of iron and nickel. And iron and nickel is a lot more dense than rock material is. So as a result, like in a planet, the more dense stuff goes towards the core. So it makes sense that iron and nickel, it would be the core of that planet. Now, since all these planets here are basically made of the same stuff, we get to see like what our planet would look like if it was busted up by studying those asteroids. So it's like, if I wanted to see where my heart and my liver and my kidneys were, if there was a cadaver and I was chopping open a cadaver and I was, seeing, oh, that's where the guy's heart is. The guy's heart's right there, so mine's probably there too. The guy's liver's right there, so my liver's probably right there too. So it kind of gives you a guide to what's probably on your inside by looking at someone else's inside. That's basically what we get here. We get to see the insides of this planet. So it gives us an idea of what's inside our planet. All right. Now, as we go down in the Earth, what we find out is the farther down we go, the temperature gets hotter, the pressure gets higher, which makes sense because the farther down you are, the more stuff there is above you pressing down on you, and it becomes more dense. Right? More dense things kind of works its way towards the bottom. Plus, there's a lot of pressure pushing on it as well. So the deeper you go, the hotter, more pressure, and more dense it is. Now, there's a chart in your reference table that shows you a lot of this. On page 10, all right, so here's the outside of the Earth, and you're working your way towards the core. So it's the very center of the Earth right there. So this chart shows you the densities. So continental crust versus oceanic crust, the densities, and you can see that as you go towards the center of the Earth, the density increases. So you got the crust on top and the lithosphere, and underneath there you have the plastic mantle and the stiffer mantle. Underneath there, the outer core, inner core, and notice it says iron and nickel, iron and nickel. So the Earth's core is made out of iron and nickel. Other things it shows you on here, it shows you where the Mid-Atlantic Trench is and the movement taking place there. Mid-Atlantic Ridge, rather, Mid-Atlantic Ridge and the movement taking place there. There's the Cascade Mountain Range and a trench, so the arrows show you how the crust is moving right there. As we move farther down this chart, it shows you what the pressure is, what the temperature is, and what the melting point temperature is. So like if I want to know what the pressure was 4,000 kilometers down into the Earth, there's 4,000. I go up to there, I come over. So it might be about 2.3 million atmospheres would be the unit for pressure. If I want to know what the temperature was 2,000 kilometers down, there's 2,000 kilometers. The temperature would be about 4,200 degrees. Right? If I want to know how deep I'd have to dig to reach to the outer core, there's the outer core right there. I dig right there, and then I come down here, so I have to dig around 3,000 kilometers or so. Now, one thing that's interesting is you notice the melting point temperature is represented by that dotted line right there. I see that the farther down I go, the melting point temperature increases until I reach there, then the melting point drops quite a bit, all right? And then it starts increasing again. Now the reason for that is, again, because this over here is rock material, but then once you get to the Earth's core, it's iron and nickel. So that's why there's a sudden difference in the melting point temperature, because you're changing from one material to another material, from rock to metal. All right, so that's the Earth's interior charts. So let's mosey on back to over here. All right, Crustal change theory. All right, mantle convection cells. Difference in heat causes convection cells in the mantle. All right, so if you remember what a convection cell is, a convection cell, we talked about them earlier in the year. So like with water, all right, if I have a hot section right here, that'll cause the water to rise. If I have a cool section right here, that water will sink, because cool stuff's more dense, so it sinks. Hot stuff's less dense, so it rises. So you end up with this circular motion taking place. That's a convection cell. Now, convection cells take place best in liquids and gases, right? Because liquids and gases move very easily. And we just said here that the mantle was a solid. However, the upper mantle is a solid, but it kind of acts like a liquid in that it can move. So just think about like ice, right? Ice in a glacier. Ice is a solid, but glaciers move because the ice can actually move. It moves much more slowly than liquids or gases do, but ice is a solid that can move. Same idea here. In the upper part of the mantle, it's technically a solid, but it's a solid that can move, so it kind of acts like a liquid. All right. So what happens there in the mantle is there's some spots that are hotter, where it rises, and other spots where it's cooler, where it sinks. So this could be like a mantle convection cell. All right, plate tectonics. Convection cells move solid crust pieces called plates. Boundaries between plates are zones of crustal activity. All right. So above, there's the mantle. The crust sits above the mantle. So here's the mantle. There's pieces of crust that sit above the mantle. We call those pieces of crust plates. So the plates are basically kind of floating on top of the mantle right there. So what happens is, if I have a convection cell like this, all right, what happens is it kind of acts like a conveyor belt. It'll make this piece of the Earth's crust move this way, all right? So the crust, the plate, is sitting on top of the mantle, and the convection cells would make that piece move that way. All right, that's what's causing the plates to move around at the Earth's surface. All right? And lastly here, isostasy. Plates float on top of the mantle. Thick plates float high, thin plates float low. Okay? So kind of an analogy I use, imagine like wood. Wood's got a density of about 0.5. Now if I had a thin plank of wood and I put it in water, it's going to float about half above the water, half beneath the water like that. If I had a big block of wood, it's still going to float half above the water, half beneath the water, but because it's a bigger block, more of it's going to stick up, but there's also going to be more of it that's going to stick down too. So that's basically what the Earth's crust is like. Ocean crust would be like this thin block of wood, where it just sticks up a little bit, but only goes down a little bit. Continental crust would be like this big block, where it sticks up a lot, but also goes down in the mantle quite a bit. All right. Now that you know what these things are, we can kind of tie them together to show you what's taking place inside the Earth. All right. So on the back of your note sheet is a diagram that looks like this here. All right, so here's the mantle right here. Here's the hot spot in the mantle where it's rising. Cooler as you move this way, so where it's cooler, it's sinking. So here's the convection cells. Okay. Now, the hot stuff comes up right there. These two convection cells are going like this. So that's going to be ripping the plate apart, the crust apart right there, and allowing the new stuff to come up. So where the plates are coming apart like that, we call that a ridge, where the plates are coming apart. And because there's constantly new rock coming up there, the new rock comes up and it pushes the old rock off to the side. So the rock's going to be youngest at the ridge, and it's going to get older as they go that side of the ridge, and it's going to get older as they go that side of the ridge. All right. Now, this is taking place. It's pulling the crust apart right there at the ridge. Now, if there's places where the Earth's crust pulls apart, there's also got to be places where the Earth's crust comes together. And where the Earth's two plates come together, when they come together, they don't just stop. What happens is one of the plates ends up going down and the other plate ends up going up. And where the two plates meet, we call a trench. Now, when the two plates hit each other, the thing that determines which one goes up and which one goes down is their density. And we just said a little while ago that oceanic crust, because it's mafic, is more dense, and continental crust, because it's felsic, is less dense. So when the continental crust and the ocean crust run into each other, this stuff's more dense, so it wants to go down. This stuff's less dense, so it wants to go up. So these two plates are going to go like this, where this one's going down and this one's going up. Now, when these two plates slide past each other, it's not like just going really, really slow like that. What happens is pressure builds up, pressure builds up, pressure builds up, then it moves. Pressure builds up, pressure builds up, then it moves. So all along where these two plates are sliding past each other, you get a whole series of earthquakes, like right there. All right? Now, when these two plates do this, again, this part gets pushed up. When that part gets pushed up, it makes mountains. Okay? And the other thing that happens is as this rock ends up going down, this basaltic rock ends up going down here, it ends up melting. So I end up with a big pool of magma, and then some of that magma comes up to the surface here and then results in a bunch of volcanoes. So a lot of times you get a bunch of volcanoes right there too. So that's why earthquakes, volcanoes, and mountain ranges frequently happen in the same areas, because a lot of it's the result of the collision of plates. They run into each other, they slide past each other, causes the earthquakes. This part gets moved up to make the mountains. This part here melts, becomes a pool of magma, and then creates the volcanoes. And to give you a better idea, a better visual, I got a short 1-minute video of this. YouTube here. All right, so we got a nice little short video here of you. Give you an idea of how this works. So there's what's happening in the mantle where it's hot. So it's rising right there. The convection cells. Got the convection cells causing the plates to move right there. Where the plates collide, you're sliding past each other. You're going to have a bunch of earthquakes right there. This rock melts, creates a bunch of magma, which works its way to the surface and makes mountains and volcanoes. So again, that's why you have earthquakes, volcanoes, and mountains frequently happen in the same location. Now there's one more chart from your reference tables I want to show you. And that is this page right here. And what this shows is various tectonic plates there are on the Earth's surface. So, like you got the Pacific plate, the Antarctic plate, the Nazca plate, North American plate, and so forth. So those are the plates that are moving around. It shows you on here where ridges are. Like right there's a ridge, right there's a ridge. Ridges are places where the crust is coming apart. Then you have trenches. There's a trench right there, there's a trench right there. Trenches are places where the plates are coming together. Right. What this also shows you are hot spots. Hot spots are locations that are really hot. They're underneath the crust, but they don't move. They stay in one spot. And you'll see what they are when we do the crustal plate movement lab. You'll see what that is. Now, where you have plates that are coming together, again, when they come together, one of them just goes under and the other one goes up. How you tell which plate is the one that's subducting and which is the one going up. If you look on the symbol right there for the converging plate, one side has little blocks on it. The little blocks mean that's the side that's going up. So for example, in the Peru-Chile trench right there, you got South America and Nazca coming together like this. Since the blocks are on this side, that means that South America plate is the one going up, and it's the Nazca plate's the one going underneath it. So whichever side the block's on, that's the side that stays up. All right. And one other thing I'll point out, there's some places on the Earth we have transform plate boundaries. So what a transform plate boundary is, the plates aren't coming together or spreading apart. A transform plate boundary is one where they're sliding past each other. So examples of that, probably the most famous one you have is the San Andreas Fault right there. So you got two plates sliding past each other. But there's also examples of that over there too. All right, so that's the chart that shows you all the tectonic plates.